ReFT, a new paradigm for parameter-efficient fine-tuning of large language models. Large language models, LLMs, have revolutionized various NLP tasks, but their sheer size often makes full fine-tuning computationally expensive and memory-intensive. Parameter-efficient fine-tuning, PFT methods like adapters and LoRa, have emerged to address this challenge by updating only a small subset of the model's parameters. However, recent work in interpretability suggests that manipulating representations directly may be a more potent approach. This video delves into representation fine-tuning, ReFT, a novel family of methods that learn task-specific interventions on hidden representations, offering a more efficient and potentially more effective alternative to traditional PFTs. The power of representations and the linear representation hypothesis. Extensive research in interpretability has demonstrated that the internal representations learned by LLMs encode rich semantic information. This understanding motivates the exploration of representation editing as a means to control and steer the behavior of these models. The linear representation hypothesis posits that concepts are encoded in linear subspaces of neural network representations. Recent empirical evidence supports this claim, showing that linguistic features, sentiment, and even logical reasoning abilities can be manipulated through interventions on specific linear subspaces. ReFT, a framework for representation. Intervention ReFT methods. Leverage these insights by learning interventions that directly modify hidden representations, rather than updating model weights. The framework defines an intervention as a tuple containing intervention function, a learned function that modifies representations. Input positions, the specific token positions in the input sequence where the intervention is applied. Layer, the specific layer in the model where the intervention is applied. A ReFT method then consists of a set of non-overlapping interventions, ensuring that interventions applied to the same layer target different token positions. This framework offers flexibility in designing interventions for different tasks and model architectures. LoRFT, a powerful instance of the ReFT family. Low-rank linear subspace ReFT, LoRFT, is a specific and highly efficient implementation of the ReFT framework. It draws inspiration from the distributed alignment search (DS) method used in interpretability research to identify linear representations of concepts. LoRFT learns interventions that operate within the linear subspace spanned by a low-rank projection matrix. This allows for targeted and efficient modification of representations, leading to significant performance improvements with minimal parameter overhead. Experimental results. The paper evaluates low-rank linear subspace ReFT or LoRFT on a diverse set of NLP benchmarks, including common sense reasoning, arithmetic reasoning, instruction following, and natural language understanding tasks. Compared to existing PFTs like LoRa, adapters, and prefix tuning, LoRFT consistently achieves state-of-the-art or competitive performance while using 10 to 50 times fewer parameters. This remarkable efficiency makes LoRFT a particularly attractive option for fine-tuning large LLMs. Specifically, LoRFT excels at common sense reasoning tasks, achieving significant improvements over other methods. For instruction following, LoRFT demonstrates impressive performance, even when trained with limited data or reduced parameter count. While LoRFT performs competitively on natural language understanding tasks, it faces some challenges with arithmetic reasoning, potentially due to the complex nature of multi-step reasoning and longer generation lengths. To facilitate the adoption of ReFT, the authors provide PyReFT, a Python library built on top of Python for training and sharing ReFT models. This user-friendly library allows seamless integration with Hugging Face models, enabling researchers and practitioners to explore the capabilities of ReFT with ease. Implications and future directions. ReFT represents a significant step forward in parameter-efficient fine-tuning of LLMs. By directly manipulating representations, it unlocks new possibilities for controlling and adapting these powerful models. The paper raises several exciting avenues for future research, like, for example, evaluating ReFT on a wider range of LLMs and tasks, including vision language models, would provide a comprehensive understanding of its capabilities and limitations. Then, the large hyperparameter search space of ReFT presents a challenge for practical use. Automating this process through techniques like meta-learning could significantly improve usability. ReFT's success challenges the traditional view of interpreting individual neurons in isolation. It encourages a shift towards understanding the contextual roles of neurons and their interactions within complex networks. Conclusion: ReFT offers a promising new approach to parameter-efficient fine-tuning, providing both efficiency and flexibility in adapting LLMs to new tasks and domains. With its strong empirical results and open-source library, ReFT is poised to become a valuable tool for researchers and practitioners seeking to harness the power of LLMs in a more efficient and interpretable manner.